continuing our journey into SQL, let's switch over to Erlang and dive right into the belly of the beast of the presentation layer. That's right, Unicode. We've all been there. But now we have a wonderful individual to help lead us through that dark place that we've all known. A fellow I'm proud to call a brother, as we have the same teacher, Mark Sugiyama, who is in the audience, and a individual who has over 6 years of experience in Erlang, help lead us through Unicode and Erlang. This is Gaurav Mitra.
Thank you so much. Hi, everyone. My name is Gaurav. I will be leading you through this dark passageway this afternoon. I will be talking about my experience working with Erlang to enable writing and reading multilingual data to SQL databases. The text is visible, right? Yeah, you're good? Yeah. We will talk briefly about the use case. Then we will see a high-level overview of the system. Then I would provide a small cheat sheet of Unicode concepts that will be useful for all of us. But we will spend the majority of our time in the learnings. Learnings that came from changing the product and the tests. The product that we are talking about here is a SQL query virtualization engine. You can think of this as VMware for databases. You can execute Teradata and Oracle queries over BigQuery, Azure, or Postgres database. So the virtualization layer really acts as if you're running a guest database on a host database. It translates requests and responses between dissimilar systems. Our customers use this to move their legacy SQL workloads from Teradata and Oracle to modern cloud data warehouses. In this particular project that I'll be talking about, our customers had a lot of Cyrillic data in their workloads, and that was particularly challenging for a couple of different reasons. So specifically, the requirement for this project was that the Teradata clients should be able to read and write Cyrillic strings into the database. So you can think of this as a SQL table here. And what is very important here is the correct representation of this data. The correct representation of Unicode data affects the sort order and the evaluation of SQL queries that you see listed here. For example, the where clause and the sort order, or if you're doing any regex operation on the textual data. It also affects how you read data from flat files into the SQL tables and how you export data out of those tables. So let's see what the system looks like. Our customers have a SQL client, which talks to the legacy database. This is what we are trying to take out here. The value proposition of the product is that you can reuse the same SQL client, speaking the same protocol. Instead of connecting to the legacy database, the SQL client would now connect to the database virtualizer. This virtualization layer is an Erlang application which decodes the incoming queries, builds a syntax tree from it, performs some optimizations on the tree, and produces a SQL query which is handed off to a modern database. When it receives results from the modern database, it repackages the results in the format the legacy SQL client is expecting and returns it. If you strip away the details here, this is what the set of components in the system look like. The virtualization layer sits in between the SQL client and the database. The SQL client is often running in a terminal application, and terminal is the source of truth. And then there is the human eye looking at the terminal. And I stress upon the terminal being the source of the truth here because sometimes in this setup, what you see is not actually what you get. We use the terminal to inspect different components in this setup. It's important to note that there are several more hops that the data, the string, has to jump through in order to get to the database and get back to the client. There are ODBC drivers sitting in between the SQL client and the database virtualizer, as well as the virtualizer and the modern database. Each of these components are places where a string encoding and decoding occurs, and hence it presents an opportunity for the data to get mangled. The twist is also that sometimes the terminal will lie to you. The terminal might show you a perfectly valid Unicode character, but it does that because it sees mangled data, which it thinks, oh, this is valid Unicode code points. I'm just going to be nice and show the user this right character. And you could be happy. My character is appearing properly. But that is often misleading. So let's take a deeper look at how data mangling can happen, but also take a mental picture of this diagram because we might revisit it during the next few slides. Oh, yes. I love Erlang in Anger. That is one of my favorite books because often when I'm debugging production issues, I am in Anger. So in the same spirit, there are some resources about studying Unicode that I go back to it when I am in Anger. These two are my favorites. One of them, the first one is a Codebeam talk, Coding for Global Languages, Unicode Char Set Strings, Binaries by Mark. And the second one is Character Symbols and Unicode Miracles by a YouTube channel called Computer File. I don't think I have ever needed anything to debug Unicode and character set issues, at least the theoretical foundations outside what these two talks contain. Really useful, I highly recommend. But when I started the project of supporting Cyrillic data sets, I did not have both of these tools available in my toolkit. So the first reaction that I had to data being mangled in front of me was being intimidated and not looking at it. Because in most cases, the result looks unintelligible. It looks like garbage. But over time, I've realized that the result is not garbage. There is something meaningful happening behind the scenes. And if I get the theory of this right, I can make sense of that garbage, and that can guide the investigation of where in that whole chain of components is the mangling of data occurring. There we go. And the Erlang shell is an excellent playground to test out these concepts. And this is also probably the most dense slide in the whole deck. The character that we will talk about here is Cyrillic O with a grave accent. On the left side, you can see output from an Erlang shell. It is started as Erl without any arguments. If you do this, the default character set is Latin 1. So when you type out the O with grave string into the Latin shell, it gives you these numbers, which at first made zero sense for me, 1054, 768. But if you coerce the shell enough, it shows you the UTF-8 encoded string, but you have to do a IO format, give it specifiers, and then you can get back the original representation. So I think it's important to make sense of these numbers. What do they represent? The 1054 that you see here is a Unicode code point. The 1054 is a decimal number. If you look at the Unicode standard, you would see it's a mapping of symbols to code points. But the code points are often referred to as U plus XYZA, 4 numbers. So that 1054 is a decimal representation of a Unicode code point 41E. 41E is simply the hexadecimal representation of 1054. So if you look up a Unicode table, you look for U plus 41E, it represents Cyrillic capital O. But oh no, that was not our original character. What this output is saying is O with a grave accent can be represented by two code points, O and the grave accent. The grave accent is U plus 0300, which is the hexadecimal representation for 768. If you note where we are in the process, we have not talked about encoding at all here. We have just translated decimal numbers that we see on the shell to Unicode code points. Encoding is the next step. If you look at a hex dump of a string file, you'd be able to see bytes. In order to get to bytes from a Unicode code point, you would need to encode the code point. Once you have those bytes, you can persist them into a file or transfer it over the network. So let's look at another example. The Cyrillic O in the previous slide was with a grave accent. It was represented by 2 bytes. The actual code point for O with a grave accent is Unicode's 043E. In this slide, if you try to locate what range, on the right side there is a table, of UTF-8 table, and if you try to locate where 043 would lie, that would be on the second row. So 043 Cyrillic O with a grave accent requires 2 bytes to be represented in UTF-8. Also remember that UTF-8 is a variable length encoding, so you can have 1-byte representations, 2-byte representations. And I think this emoji, 128512, the smiley face, is probably a 4-byte representation. You can also play around with this in the Erlang shell. What helps is if you start it with a plus PC Unicode argument so that the shell knows to expect multi-byte characters. When you do that, and if you paste, if you mention a list which says 65, 1056, 8364, 128512, the shell is now ready. It knows that you can have multi-byte characters, and it translates it into the right symbols for you. What is also helpful is understanding some of these functions. In the Unicode library, the Erlang Unicode module, the function characters to binary is something that I often use. I come back to it often because here you can take binaries or lists of code points, mention the input encoding as the second argument, and the output encoding in the third argument. So if you do that to the list that we just talked about, say, hey, characters to binary, this sequence of code points I know is encoded in UTF-8, but please also encode it into a binary of UTF-8. So it comes back as it is the same output, but it now has the UTF-8 encoding that's specified in the binary. But if you switch this up a little bit and say, oh, no, I want the out encoding to be Latin 1, it throws an error. And the error is really useful here. It is an error tuple. It is a partially converted binary. And remember, the output encoding is Latin 1, so it sees the A, which is 65. It says, yes, this is valid Latin 1. I'm going to go ahead. It sees 1066, and it said, not Latin 1. I'm just going to stop the conversion. In many cases, when you're doing, when you want to determine what encoding a value is in, that's the behavior that you fall back on. If you try to convert a UTF-8 value to Latin 1, if it fails, it's a UTF-8 value. That is a lot of information in a couple of minutes. Questions, concerns? Mm-hmm. That is a very good question. I suspect, I know why B is getting displayed because the shell is started in the Unicode mode, and it is, when it is coming out to the display, it says, yeah, this is valid UTF-8, let's display this. I do not know why they are not doing it for the multi-byte characters, because the smiley sign is in the third and fourth row of the table on the right side. Good question. Let me get back to you on that. Or if someone in the audience has the answer, I don't know. All right. So what changes did we do? UTF-8 is the encoding standard that is clearly replacing every other alternative, and thank God it is replacing every other alternative because it has backward compatibility with the Latin 1 and ASCII standards. It's variable length, so it utilizes less space than other encoding which covers the Unicode standard. So whether you're working on a feature on an existing system or architecting something new, UTF-8 compliance is the way to go. And spreading this awareness in your team is very important. That's been our learning, that if everyone in the team is not aware of the best practices, sometimes you'll end up with weird ways that string modules will behave, and down the line, if you have to support, let's say, Japanese or other languages in the Unicode standard, not designing the libraries according to this knowledge might make your life harder than it needs to be. Also, understanding these concepts will help you look at the mangled data and first not be intimidated like I was, and figure out which part of the data is getting mangled. Because once you narrow down sections of the data which are getting mangled, you can map it to certain sections of the Unicode standard where the problem lies, and then you can look at your components and figure out, oh, maybe you are the one mangling this up because you're not handling this range well. Like the question here was, why is the B getting displayed and not the smiley face? So no, I know what to look at now. I can look at that feature and try to map it with the third line of the UTF-8 standard encoding scheme and figure out what's happening. And sometimes your tools will lie to you because they will try to unmangle the data for you. And if you are trusting the visual representations of things to lead you down the right path, that might be a that might make life difficult. What also helped us was consolidating a lot of our string operations into one module so that we are not calling the Unicode module from the code base all over. And if you're doing that, the only way to debug the product is probably doing some sort of trace that, hey, this function was called from 5 different places, and then your logging libraries are also calling it. Staying away from that and consolidating everything into one module has helped. But there are 2 clusters of changes that were very instrumental and gave us the biggest bang for the buck. One is preserving the metadata, and the second is not guessing the encoding of things. So preserving the metadata means, one, if you have context about what encoding the string is in, please try your best to preserve that, because bytes are just bytes. If you're trying to encode, if you have a partial decoding of a string and it fails, it's not that probably it's invalid, it's just in a scheme that you don't understand yet, and the only way to carry that context information is having metadata around. It's also helpful to normalize strings. Once, what we have done in our code base now is that once a string enters the virtualizer system, everything is in UTF-8. And as a last resort, if you really can't do those things, carry an auxiliary structure which keeps the metadata going along with it. Also, even though the Erlang docs mention things like, here is a way you can determine the encoding of the string on the fly, try not to do this, because sometimes you won't be there to sort of shepherd your code base all the time. And if there isn't enough awareness about UTF-8 among the team, sometimes what we have faced is that all UTF-8 characters are not valid Latin 1 characters, but all valid Latin 1 characters are valid UTF-8 characters. And if you decide to use on-the-fly inference of encoding like this, often what people end up doing, oh, this is UTF-8 and this is Latin 1. These are 2 separate code paths for processing these 2 things. So try and avoid that. Or at the very least, educate the team about these things, because we like our lives simple. This helps. Also, exchanging the metadata is really something that you should do earlier in the process. There is a stage where a SQL client connects to the server, and the server will advertise, hey, these are the character sets I support. Client, you can pick something from that set. That's the point where you get the information for the encoding, and then you sort of hold on to it for the entire session. There is another catch here. Sometimes clients will say, I want Latin character sets, but they will not specify it more. They will not say it's Latin 1 or Latin 9. And the key difference here is that the euro sign that we love, it was introduced in Latin 9, is not part of Latin 1, but sometimes SQL clients won't tell you the difference. They'll say, here is a euro sign, and it's a Latin encoding. Also, the Erlang Unicode module uses Latin 1 for encoding and decoding. So when we were dealing with the euro sign that was slipped in by a Latin encoding, we had to manually patch up the UTF-8 encoded values. I would love to see Latin 9 being a first-class citizen of the Erlang Unicode library. If you think it's a good idea, please come talk to me after the presentation. I would love to have more support for that. And the last section is testing. Remember the diagram about what you see is not what you get, and the different components that are in the way of the data getting in and out of the system. What has helped us make correct product changes is that We have made all of those components configurable using Terraform, and we have learned some things that were not super obvious, because the encoding of the input files that are fed to a bulk load process or export that's coming out of the database, they have encoding attached to it too. So if the encoding gets mangled in the beginning, it's very hard to figure out what's happening later. So look at all of those checkpoints, make sure you explicitly know what encoding the data is in, and do not trust the defaults. Sometimes the defaults are UTF-8, sometimes it's Latin. Trust but specify. In a world of Unicode where tools are lying to you, sometimes tools are hiding things to you, the only source of truth is hex, because we know hex don't lie. And in the data, in flat files, you can see the hex using a hex term -c, and you put the file as an input to it. In the database, you can see the hex of a value like something like this using a convert function. No matter what display device you're using, what tools you're using, you can always rely on the hex value to give you the correct representation of what the data actually looks like. Thank you for bearing with me through that dark passage. Questions? That's all I have for you.
I don't know if we have time for questions, but that was
right.
just a wealth of knowledge. I mean, talk about Labyrinth. You've just handed out tool after tool, on a difficult subject. So thank you. Please, congratulations.
Thank you so much.